Hi, my name is Niklas Hohmann and I'm a paleobiology student at the University of Erlangen. In this talk I will try to unify three seemingly completely different things. The first is the reconstruction of extinction rates. The second is modeling time averaging. And the third one is image processing. So I will start with the reconstruction of extinction rates.
So the thing about extinctions is that we can never observe them directly. We can only use indicators for extinctions. And a common indicator for an extinction is the last fossil occurrence of a taxon. And it will always predate the actual extinction, and this is commonly called the Signor-Lipps effect. And this can be modeled by a relocation of the actual extinction to generate the last fossil occurrence. This motivates the following model. There is an extinction rate given, and this extinction rate generates the extinctions. Then the extinctions are relocated by the Signor-Lipps effect to form the last fossil occurrences. These fossil occurrences are collected and documented in the field and can be used to reconstruct the rate of last fossil occurrences.
So this naturally raises the question whether there is a connection between the rate of last fossil occurrences on the one side and the extinction rate on the other side. And this is where image processing comes into play.
One common effect in image processing is a blurring effect, which is demonstrated by these two pictures. And one of the most common blurring effects is the so-called Gaussian blur, which is based on a mathematical operation called a convolution. I will show how a convolution works on this diagram. It represents the same thing twice. At the bottom, there's the representation in terms of image processing, where we can see one single pixel, and at the top there's the intensity of blackness in this picture at the bottom taken as a function, where 0 represents white and 1 represents black. The convolution is based on a so-called convolution kernel, which is simply a function that determines how the actual smoothing of the picture will take place. In this case, it is a normal distribution, and if we perform the convolution, we will get a blurred picture, which is a blurred pixel at the bottom, and also a function that is like a normal distribution at the top. Of course, this also works for a much more complicated picture. This is a function I generated with a random number generator, and it is also being nicely smoothed by the convolution kernel. Now let's go back to the extinction rates, looking at a single spike in extinction rate. And this can also represent it as a picture where black is a very high extinction rate and white is an extinction rate of 0. And with some math, it is actually possible to show that the last fossil occurrences are a blurred version of the extinction rate. But the convolution kernel is not a normal distribution, but it is this exponential decay we see here in the left picture. And again, the same principle can be applied to a very, very complex extinction rate simply by convoluting the extinction rate with the exponential kernel, and we get what we then actually observe in the outcrop, which is our last fossil occurrences. This can be used in a variety of different ways. Here, for example, the same extinction rate is combined by different exponential kernels with different parameters that are commonly denoted lambda. And this lambda corresponds to how many fossils do we find in the field. So lambda equals 4 corresponds to 4 fossils found per time unit in the field. And you can see how the actual extinction rate is approximated the more fossils we find in the field. But if we find very few fossils in the field, nothing remains of that sudden spike in the extinction rate.
So with the model for extinction rates available, we can now turn to time averaging. But let's first look at what time averaging is exactly. One of the fundamental principles of geology is that we find younger objects further up in the stratigraphic column. However, there is more and more evidence that this does not necessarily hold, and you can find shells of different ages alongside each other in the same bed. And this is called time averaging. Just like extinctions and last fossil occurrences, time averaging can also be modeled as a relocation of shells. This is done by assuming that the shells were deposited with the oldest shell at the bottom and the youngest shell at the top. And then these shells were relocated into a time averaged bed that we observe in the fossil record. With this, a similar model to the one for extinction rates can be built, and that is, we have a rate of fossil occurrences that will generate our sample. This sample is then relocated by time averaging to form a time averaged sample, and from this time averaged sample we can reconstruct our time averaged fossil occurrences.
This model shows that time averaging can also be modeled by a convolution, just as the relation between last fossil occurrences and extinction rate can. However, it is not clear how the convolution kernel in the case of time averaging is. Actually, evidence points towards two different convolution kernels. One is a exponential kernel, just like the one used for extinction rates. The other one would be a uniform convolution kernel. And here you can also see a single spike in fossil occurrences and its time averaged signal after a convolution with a uniform kernel. And again, the same can be done for more complex functions of fossil occurrences. Here there's two spikes in fossil occurrences, and for this there's different types of time averaging. So the higher the number b, which is shown in the legend here, the stronger the time averaging is. And you can see for b equals 5, none of the original two spikes are actually visible anymore, and the original signal has been averaged out of the fossil occurrences and is not visible.
So far, we have learned that the convolution can be used to model time averaging and to derive the rate of last fossil occurrences from the extinction rates. But it can also be used to actually reconstruct extinction rates from the rate of last fossil occurrences. And this is where an operation called deconvolution comes into play.
Just as subtraction reverses the effect of addition, the deconvolution reverses the effect of a convolution. This is why deconvolutions are common in image processing when it comes to reversing a blurring effect or making images sharper. So with the models built in this talk, a deconvolution has the potential to actually reverse the effects of the Signor-Lipps effect and to reverse the effects of time averaging on the patterns we see in the section to reconstruct the original signal we are actually interested in. Deconvolutions are common operations in image processing. There are many good algorithms for deconvolutions available. However, it is so far unclear which of these algorithms are most suitable for the problems we have in geology. So in this talk I have shown how to model time averaging and how to model the rate of last occurrences, and also sketched a possibility to reverse the effects of time averaging and reconstruct extinction rates from the rate of last fossil occurrences. However, it must be emphasized that the model I was using here is extremely simplified because it does not include the effects of changing deposition rates on the fossil occurrences as we find them in the section. If you want to know more about how these changing deposition rates alter these fossil occurrences, I highly recommend watching my other talk, which tackles exactly that topic. And I would also like to thank my supervisor, Emilia Jarochowska, for her constant support, and also Adam Kocic for his input on the preprint on which this talk is actually based. The DOY number of this preprint can be found here, and if you're interested, just have a read, and if you have any questions, feel free to write me an email.